Okay, so I just want to start by saying that I'm originally from Trinidad and Tobago in the Caribbean. So Trinidad is a Caribbean island. And I have to tell you all this because people say they missed the first part of my talk trying to guess where I'm from. So now you know I'm from Trinidad, I have your full attention. I also want to thank you for being part of the first adaptive experiment. So instead of just my title slide, I said, why don't I tell you what the whole talk is about? So the title of the talk is self-explanatory. I hope to show you how I'm using adaptive experimentation to design real-world systems for education and health. And here's the key problem. It's too difficult to run rigorous real-world experiments with the scale and speed to improve technology. And the approach here is AI-driven adaptive experimentation. So where would experimentation be useful? We all care about AI for social good. And there are three areas I've worked in. In education and lifelong learning, AI is hurting learning for many students, but it could be helping. In mental health, we have huge problems with 1 in 5 people experiencing a mental health challenge. But you've heard about all the horror stories about AI. How do we design AI so it actually improves people's ability to manage negative emotions? In physical health, inactivity risks avoidable diseases for 1.8 billion people. How could AI actually get people motivated to get them to exercise and be healthier? Now, the problem is, AI is helpful for some people some of the time. But other times, it's ineffective or even harmful. So how do we figure out when it's hurting, helping, or having no effect? This is where experimentation can be helpful. I'll give you one example. Let's say we take an AI coach that we built. This was to get people to exercise more. And let's take a piece of it. It might be helping some people, but maybe not others. And let's actually run an ABN experiment. Let's generate a different version and give it to 50% of people. Like, how would a walk make you feel better? Text back when you go. Or maybe there's a better idea. 50% of people can get another message. When could you go for a walk today? And the idea here is we're not just relying on our intuitions. We're actually randomizing people to see which of these actually result in more people walking. Now, A/B experimentation has driven billions of dollars in business value. It's foundational in science in the form of randomized controlled trials. But you know there's a but, right? We've run over 500 experiments with over 500,000 people. And here are the problems we see. Experimentation is underused for real-world social good. When you run an experiment that tests buttons, it can mislead you or it can help you. Some experiments get published in Science. The challenge is designing really good experiments in the context of social good. The difficulty is it's hard to run rigorous real-world experiments with the scale and speed we need to. So we develop adaptive experimentation methods to test more ideas rigorously at scale and speed improvement and personalization. Here's an example. How do we speed up adding and removing ideas? Start with an app like what I showed you, and let's actually use human LLM co-design to generate different versions. Then we actually deploy these versions to 50% of people, let's say, and we get user data. But after that data, we might get some evidence. For example, we might say that it looks like actually message 1 is better. Let's give it a 30, message 1 is less good. Fewer people walk. Let's give it to 30% of people. And message 2 is actually better. Let's give it to 70% of people. So what you're doing is you're using data in real time to give people what's more or less effective. Now, why that's good is as you're removing ideas, you can add new ideas in. So you can now actually re-rate your experiment where you now give people, just a few people, what's seemingly least promising, give more people what's looking good, and then keep adding in new options to test it out. What that means is over time, as you get more and more data, you can adjust your experiment to phase out what's working and add in what is. And then basically you get to an option where you might give people what's best for everyone. Does that make sense? Of course, we also want to discover how to personalize. What's best for you might not be best for me. In this image, think of the green group, like people who exercise a lot, and the orange group, people who don't exercise much at all. Message 1 might work better if you exercise a lot, but actually message 1 is worse if you don't exercise. Message 2 is better. So we want adaptive experiments to be able to discover how to personalize, so we give people what's best for them. So let's summarize this. This is the kind of key point. Take any app, any interface, any website, take a component, and generate different versions using human LLM co-design. Then deploy these in the real world and start actually analyzing data using reinforcement learning to figure out what's the probability a message is good for someone. Let's give it to more and more people so we can keep improving what's happening. This can also now lead us to do personalization, where we discover what's best for different people at different points in time. Does that make sense in terms of the approach of adaptive experimentation? And is it clear how it applies everywhere? Everything we do has better alternatives. Adaptive experimentation can help you find them. So our adaptive experimentation framework was fortunate in winning the $1 Million X Prize for the future of AI-driven experimentation. And we received a $3 million NSF grant to provide access to tools and methods that any of you could use. In particular, there's 6 fields that I work in where scientists and practitioners can now actually use these tools to advance their research questions and have more real-world impact. So I've used adaptive experimentation to establish substantive research programs in each of these 6 fields. And I think of each as having at least 10 papers in them. So human-computer interaction, design technology for people. AI in the sense of interfaces for using LLMs and Gen AI. AI in the sense of novel reinforcement learning algorithms that will analyze data in real time. Statistics, coming up with new analyses for these kind of adaptive experimentation methods. And combining computer science with health and computer science with education. So I think of myself in working in all of these. But if you have to pigeonhole me, you can just choose your favorite. So to sum up the talk so far, I spent a while explaining the problem and the approach, trying to speed up running experiments to have impact using adaptive experimentation. In the first part of the talk, I'll talk about generating, testing, and improving interventions using examples from education. I explain how we can do human LLM co-design more effectively, and how we can actually test and improve educational interactions using adaptive experiments. I'll then give examples of personalizing interventions in health, how we can use LLMs to personalize mental well-being stories, and then actually personalize messages for exercise using adaptive experiments. Although I give you examples in education and health, I chose these because each of these connects to 6 papers in the different fields I mentioned. So they might be in education and health, but they all correspond to papers in human-computer interaction, developing new algorithms, and other areas. So let's start on this part. By intervention, I mean any set of actions that can change behavior. Think of an interaction with an educational chatbot. An intervention could be the entire AI system, option A1 versus A2. But you could actually be more fine-grained and rigorous. An intervention could actually be the prompt and context you give to an AI system. So you want to randomize these and figure out which of these is effective. Or it could actually be a sequence of interactions with an AI system. So the idea here is that we want to be able to think carefully about what level to compare interventions at, to see if we can figure out what's effective and how to improve it. It should also be clear that you can apply this to anything. For example, think of teaching in Canvas. You could do interventions where you experiment with sequences of web pages or assignments to see what's helpful. Or you could get very precise and think, let's say a student attempts a problem, and they get the answer. If you were there with them, what would you say to them at that moment in time? That's an intervention. What explanation would you give them? And how do you figure out if that was actually the best option? So one of our contributions was a system we published at CHI, Computer-Human Interaction, and it was a system to allow anyone to go into Canvas and actually test out different ways of explaining concepts and communicating to students. Now, the system also allowed us to gather contributions from students, not just instructors. So you've got instructor ideas, and now how do we get ideas from students? So I developed a theory of learning which showed that telling students to explain why an answer is correct could actually help them learn. maybe even more than you telling them why. So the idea is that when a student has to explain why an answer is correct, they go beyond memorization to understanding what's the key principle. So we told students to explain why the answer was correct. And then we took the explanation, and if it vetted it according to some criteria, and the student thought it'd be helpful to other people, we could then actually add it to the pool. So we have a method now of increasing the size of our experiment. Of course, we can also elicit ideas from LLMs and add these to the pool. And another system we built was called AB Scribe. And what we did is develop a workflow where we could actually get LLMs to take as input ideas from students and instructors along with instructions and figure out how do we actually design better versions of these through a coordinated workflow. And we found in that user study that people found that this AB Scribe system gave better variations than ChatGPT. So it was a way of actually coordinating better generation of versions that were more diverse and more effective at what they want to get across.
Sorry, can you say again, how did you generate the, like one of the reasons you might want LLM explanations is they're very quick and easy to generate. Are you fully using just human labor to generate the alternatives that you say are better?
So we're using all of those. And so this is like a multi-stage workflow, but the key idea is this. In this setting, LMs are very good at generating things, you're right, but often these things are not that high quality. So one approach we use is actually to get LMs to generate a version, and that often gets instructors to generate better versions.
Using the LLM one as like a starting point.
Exactly, that's one way we did it. Another way, though, is, of course, when you get ideas from instructors or students, giving those as input to the LMs is helpful, because it kind of seeds it to what's part of the space to be in. You can also ask the LM with more detailed information. Here's what the pros and cons are of this explanation. It touches on this key principle of learning, but also actually gets students to generate things themselves. So you can actually get pretty creative. So for example, when I use LMs, I often prompt it with things like this. Here's a scientific paper on how people learn by explaining. Use this and other related research and coming up with different options. Does that make sense how AB Scribe is a tool for combining all of those different points of interaction? Okay, so now we have this setting, right? We've got a good method for continually adding explanations. But how do we actually now remove them in real time so we get the best options? So the key idea here in this adaptive experiment is as we're giving people options, we want to analyze data. For example, if students rate an explanation as helpful or not. And here's the key idea. The probability of assigning an explanation, A1 versus A2, is based on the probability the explanation is best, such as being most helpful. So I'll say that again, that's very important. The probability of assigning an option is based on the probability that option is best. So for example, you can think of a randomized experiment as having a prior belief. We don't know what's better, so we're 50-50. But after we get some data, we shouldn't be 50-50, right? We should have some evidence that one might be better than another. So maybe there's a 30% chance that message 1 is better than message 2. So what do? We assign 30% of people. And this means we can actually add in new versions over time. Like we might add a third version. And the nice thing about this framework is you can actually incorporate qualitative information and expert knowledge. For example, we will assign this one 40% of the time, not because we necessarily think it's that good, but because we'd like to collect data about it. This one gets low probability because we've seen evidence it's not that promising. But it's still collecting data, and if we're wrong, it can come back. And so this is a setting where we can incorporate instructors' perspectives and their prior knowledge. And the idea is we're now changing probabilities over time. Does that make sense? Now, as we get more data, what do? Again, reweigh the probabilities. Maybe there's a 2% chance this is best, and a 73% chance this is best. So now, give it to 2% of people or 73% of people. And so ideally, we're converging towards giving people what's best. So you start at 50-50, and you end up giving something most of the time.
Questions?
Yes.
One, how do you choose the percentage for the new option? And then two, like if you're asking a bunch of students which response is most helpful, I would imagine most of the time you don't converge to like one answer.
Yep.
You converge to a distribution. So can you comment on that?
Yes, so it's two great questions. So the second part is personalization. I'll talk a bit more in the second part of the talk. And the idea here is, again, very powerful, I think. What's the probability of assigning the option? it's a probability that option is best. But now you have data about the students. So the probability of assigning it is based on, for example, the level of knowledge or the experience with the topic. So it's the same conceptual framework, but now the algorithm you use will be different. Okay? In terms of how you incorporate these, that's again trying to use like different processes for eliciting input from instructors and from scientists. That's how we set those probabilities, and it does require some qualitative work. But more broadly, I think the question is this. How do we choose these probabilities? I think that's something we can have decades of work on. How exactly we have particular statistical models and algorithms to choose these probabilities. But let me give you one example. Just checking, is this overall framework clear to everyone? Makes this kind of foundational for the talk. Probability of assigning an option is based on probability that option is best. And it allows you to keep exploring new options, but also take what you're doing and putting it into practice. So in this case, we formulated as a multi-arm bandit problem using the algorithm Thompson sampling because it's interpretable and allows particular affordances in interacting with it. I should say we actually often use variations of Thompson sampling because we find issues when you deploy this in the real world. Despite people saying for decades it's great for experiments, there are a lot of issues that come up. But I'll give you a simple example here. So in a multi-arm bandit problem, right, you have a set of actions, in this case arms, like assign intervention A1 or A2 to a participant. For example, exclamation A1 or A2. And you're measuring the reward, the thing you want to maximize, or the outcome, like whether the participant rated exclamation is helpful or not. Now, what's your objective? You want to maximize the total reward across all participants. And here's an algorithm that aims to do that. The key idea of Thompson sampling is this. Let's assign actions proportional to the posterior probability of being the highest reward given the data so far. So again, 50-50 or 30-70, there's a 30% chance this is the best option given the data so far. So I'll just go through this quickly. But when you run Thompson sampling, you're going to work from a prior belief. So each explanation has a prior distribution that summarizes the evidence about its success. So you might use a beta distribution where the parameters are a number of successes, a number of failures. So think of this intuitively like this. Exclamation 1, if it was something like beta 1,1, that would be uniform. It would say, I have no idea what the probability is that someone else thinks is helpful. It could be 0.2 to 0.8, so we're unsure. If exclamation 2 had a beta like 8 and 2, it would mean I've seen 8 thumbs up on this exclamation and 2 thumbs down. So basically, these beta distributions, in a very intuitive way, using conjugacy, capture the evidence that something is effective based on how many times it's been successful or not. So by using the Bernoulli reward, we get conjugacy here. And so with Thompson sampling now, you draw samples from the model parameters, in this case a random sample from each arm's posterior, and you assign the arm whose sample is highest. And now you get to update your posterior. After observing the outcome, update the success failure counts for the selected arm. So we can always come back to this later, but the key idea is this. It's a beta Bernoulli distribution that captures for every explanation how confident you are that it's going to have a high success rate. And by running Thompson sampling this way, you're approximating that arms are sampled based on the probability that they're the best option. So we deployed Thompson sampling in an interpretable system in Canvas. You all could have used this if you're part of our study. So 3 instructors at Harvard use this. So what's interesting is this is running in their course. And while it's running, they don't have to analyze data, but they can monitor what's happening. So exclamation 1 against 2, the probability might be 0.23 versus 0.77. They can see how it's based on the student rating so far, 7.26 versus 7.48, or the number of students, 46 versus 56. And so we found that actually this was quite effective because instructors were able to actually test more than one option. Instead of just having to decide that I think this is the best, let's give it 100% of students, they could actually run this in real time. And in particular, they found it helpful because it would give students answers that are more helpful. So when early people give data, it actually helps improve the experience of